Welcome to The Explainer. So you've heard all about zero trust, right? The whole never trust, always verify mantra. It sounds pretty suspicious of, well, of everything. But that brings up a really big question. If it's designed to trust nothing, how does it ever actually say yes? Today, we're cracking open the brain of the whole operation, the trust algorithm.
All right, so let's just dive right into that central paradox, the big question mark at the heart of zero trust. The entire philosophy is never trust, always verify. It's right there in the name. But think about it for a second. If you literally trust nothing by default, how do you ever let anyone in? How does a system that starts at a hard no ever get to a confident, yeah, okay, you're good to go? Well, the answer, and this comes straight from the official NIST guide, the book that basically wrote the rules on zero trust, is something called a trust algorithm. And I love their analogy for it. They say to think of the whole system, the policy engine, as the brain. And this algorithm, that's its thought process. It's the secret sauce, the logic that takes a whole mess of data and spits out a simple decision.
So here's what we're going to do today. We're going to deconstruct this brain. We'll look at the inputs it uses, kind of like it senses. Then we'll get into how it actually thinks. And there are a couple of different ways, like a simple checklist versus a more complex scorecard. And finally, we'll wrap up with why this whole thing is such a game changer for cybersecurity.
All right, let's get into it, the zero trust brain. So the official, fancy term for this, the one you'll see in the NIST documents, is the policy engine. But its job is actually super simple, at least on the surface. It does one thing, and one thing only. It decides whether to grant or deny access. It's the ultimate digital gatekeeper, and its entire judgment call comes down to what that trust algorithm tells it to do.
But a brain can't make a decision in a vacuum, right? It needs information. It needs senses to understand what's going on around it. So let's take a look at the different data streams that are constantly feeding this algorithm. Think of these as its eyes and ears on the network.
And this is a great way to picture it. You've got all these different streams of information, all these different signals, and they're all flowing into this one central point, the trust algorithm. And out the other side comes that simple, critical decision, grant or deny. So let's actually break down what these inputs are, one by one.
Okay, first up, input number one is the request itself. This is the most basic piece of the puzzle. The algorithm immediately asks, who are you? What computer are you on? And what exactly are you trying to get to? And the little details here are huge. Things like your operating system version, or whether you've installed the latest security patches, because an out-of-date device is basically a welcome mat for an attacker.
Next, it doesn't just take that request at face value. It checks it against the subject database. And listen, this is way more than just checking a username and password. We're talking about understanding who this person is in the organization, their role, what they're supposed to be able to access, and, this is the really cool part, their history. The system is constantly asking, hey, does this look normal for this person? Is this consistent with what they usually do?
Then, the device itself goes under the microscope. The algorithm dives into an asset database to figure out, is this a company laptop or some random machine? It checks its health, its overall security posture, is the antivirus running, are there known vulnerabilities? You get the idea. Any sign of an unhealthy device is a massive red flag.
Of course, the algorithm also has to think about the destination. I mean, what is the user trying to get to? Think about it. Asking for access to the company's public homepage is one thing, but asking for access to the payroll database? That's a whole different ballgame. The more sensitive the data, the higher the security bar is going to be set.
And last but definitely not least, the algorithm looks at what's happening right now. It's pulling in live, real-time data. We're talking about threat intelligence feeds, alerts about new malware that was just discovered, and it's also scanning internal system logs for any weird activity anywhere else on the network. This makes the decision incredibly relevant, like up to the second relevant.
Okay, so we've got all these data streams flooding in. It's a ton of information, right? But just having the data isn't enough. How does the brain actually, think? How does it process all of that to make a call? It's not just about what it knows, it's about how it thinks.
And this really breaks it down into the two main ways this brain can think. First, you've got the checklist model. This one is super straightforward. It's like a bouncer at a club with a strict list. If you fail even one check, you're not getting in. It's a simple pass or fail. Then you have the scorecard model. This one's a bit more nuanced. It looks at everything and assigns points. A healthy corporate laptop might get you 50 points, but coming from a weird location might subtract 10. If your total score is high enough, you're in. It's more flexible.
Okay, but here's where it gets really powerful.
The magic of this algorithm isn't just in making that one decision when you first log in. The thing that truly separates Zero Trust from the old way of doing security is its ability to understand context and its refusal to ever stop paying attention.
And this is a really critical difference. The old way treated every single request as if it had amnesia, like it was the first time it ever saw you. But a contextual evaluation remembers. It builds a baseline of what's normal for you. So let's say you usually access 10 documents a day. But then one Tuesday at 3 a.m., your account suddenly tries to download 1,000 files. A singular system might just say, well, the password is correct. But the contextual algorithm is going to scream, whoa, 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 this is weird, and flag it immediately.
And this all happens in a non-stop loop. It's not a one-and-done check. You request access, the algorithm runs its numbers and lets you in. Great. But that's just the beginning. The system is watching that entire session. And if anything changes, literally anything, like you connect to a sketchy Wi-Fi network, the algorithm immediately reruns the numbers. Trust is reevaluated right there, on the fly.
And that really brings us to the core takeaway here. In the world of Zero Trust, trust is temporary. It's not a permanent badge you earned. It's more like a temporary visa, granted for one specific trip, and it can be revoked in a heartbeat if anything looks off.
So we've gone through a lot here. Let's boil it all down. What are the absolute key takeaways you need to remember, whether it's for an exam or for a real-world job interview?
Okay, 4 big ideas to lock in. First, trust is never, ever just assumed. It is always calculated on the spot. Second, that calculation is based on a whole bunch of different inputs: who you are, what device you're on, current threats, you name it. Third, the way it calculates can be that strict pass-fail checklist or the more flexible point-based scorecard. And finally, and maybe most importantly, trust isn't permanent, it's temporary, and it's being checked and rechecked over and over again.
And all of this leaves us with one last big question to chew on. As these algorithms get smarter, faster, and more automated, what happens to the human's role in all of this? I think it means the job changes. You stop being the person manually checking IDs at the gate, and you become the architect who designs the super smart automated gatekeeper system. And that is the future we all need to be ready for.